I instructed an AI model to write a production-ready HTTP server in Go. The prompt specifically required JSON API endpoints, request ID propagation, structured logging with slog, and graceful shutdown handling. I asked for the complete, professional-grade checklist. The output it generated is structurally immaculate. The handlers compose perfectly through the middleware chain. It compiles on the first attempt, passes every unit test, and triggers exactly 0 linter errors. By every static measure of code quality, it is ready to ship. We will deploy this code onto a machine capped at 4 CPU cores and 2 GB of RAM. This matches the strict physical constraints of a standard Kubernetes pod in a realistic enterprise environment. At a low load traffic rate of 100 requests per second, the server operates without breaking a sweat. The median response time hovers at 1 millisecond, and the 99th percentile latency sits at an invisible 3 milliseconds. This is the load level where every AI-generated demo looks flawless, but staging environments typically run at 1 to 5% of actual production traffic. When a system is under stress, critical architectural flaws remain entirely hidden by the runtime environment. To find those flaws, we instantly scale the traffic to 10,000 requests per second. The physical constraints remain the same, but the volume of incoming data hitting it is now massive. This chart plots our response times under heavy load. Notice the flat baseline that suddenly begins sawtoothing with extreme volatility. At the 15-second mark, our p99 latency spikes to 58 milliseconds, and the instability never recovers. The median response time, the p50, is still sitting at a very fast 2 milliseconds. Most individual users are getting a fast response, but the 99th percentile metric proves that the top 1% of our traffic is experiencing severe delays. 1% of 10,000 requests per second equals 100 slow responses every single second. If this service sits in a critical path, those 100 delayed responses pile up, exhaust connection pools, and trigger cascading timeouts in downstream services. The source code itself is logically correct, but the runtime performance is failing. An AI model analyzing the syntax cannot predict this failure, because resolving it requires empirical profiling of the running system. We need to observe the raw behavior of the Go runtime as it processes the load. The first diagnostic step is restarting the server with the geodebug GC trace flag enabled. This graph maps latency spikes alongside trace data. Vertical markers show garbage collector fires. Notice the direct alignment. At 10K RPS, the collector runs 20 times per second, matching our spikes. Go's garbage collector works concurrently, but requires 2 brief stop-the-world phases. During these phases, every Go routine pauses. If a request is executing when that pause occurs, it freezes mid-flight, absorbing that entire pause time into its latency. The slow requests driving our p99 spikes are not executing complex logic or waiting on bad database queries. They are simply the unlucky requests trapped by aggressive memory management. To stop the garbage collector from firing 20 times a second, we must locate the specific lines of code generating the memory pressure. We use Go's built-in pprof heap profiler to capture a snapshot of all active allocations. This table isolates our top memory allocators. The standard JSON serialization function sits at the absolute top. Every time we call json.marshal, it uses reflection and allocates a brand new byte slice buffer to write the payload. At low load, allocating a few kilobytes per request is entirely invisible. At 10,000 requests per second, we are generating 10,000 new buffers every second. That equals tens of megabytes of garbage created and immediately discarded continuously. The second major hotspot is our structured logging middleware. The AI followed idiomatic tutorials, calling slog.with to append request IDs to every log line. Under extreme load, this creates thousands of short-lived logger wrapper structs per second. Finally, we see allocations from the HTTP middleware chain itself. To log the outgoing status code, the AI-generated code wraps the response writer in a custom interface. Because this interface is passed down the chain, the Go compiler forces it to escape to the heap, creating another persistent per-request allocation. Individually, these are standard, idiomatic convenience patterns. But at extreme scale, these tiny repeated allocations compound into massive garbage collection pressure. This flame graph maps our CPU execution time. The widest blocks represent memory allocation and background garbage collection. Up to 20% of our total processing power is spent acting as a memory janitor, rather than serving actual requests. We can eliminate the JSON buffer and response writer allocations mechanically using the sync.Pool pattern. Instead of allocating new memory for every single request, we maintain a persistent pool of reusable objects. When a request arrives, the server retrieves an existing buffer from the pool. It writes the JSON payload, serves the response to the client, scrubs the buffer clean, and drops it back into the pool for the next request. For the logging hotspot, we optimize by shifting when the work happens. Instead of allocating a new logger struct on every incoming request, we configure a custom handler to extract the request ID directly from the context only at the exact moment an error or log line is actually written. The application logic remains untouched. The performance gain comes solely from reducing the friction between the code and the Go memory allocator. With the code optimized, we address the runtime configuration. By default, Go triggers a garbage collection cycle whenever the heap doubles in size relative to the live data. At high throughput, a small heap reaches that doubling threshold rapidly, forcing aggressive collection cycles. We can override this blunt default behavior using the GO_memLimit environment variable. This allows us to establish a strict maximum memory cap tailored directly to our 2 GB Kubernetes pod constraint. We set Go_memLimit to 1.6 GB, allocating 80. Our p99 tail latency has dropped from 58 milliseconds down to a highly stable 7 milliseconds. That is an 88% reduction in tail latency under maximum production load. We achieved this massive performance gain without rewriting a single line of business logic or altering the core feature set. The application remains exactly what the AI initially built. But by observing the runtime under load, we've aligned its internal behavior with the physical limits of the server. This investigative process provides a repeatable framework for solving scale issues. It begins with a high-load baseline, uses GC_trace to correlate latency spikes with system pauses, and isolates the source code using heap and CPU profiles. You follow a strict mitigation hierarchy. Eliminate the highest volume allocators first, apply object pools for per-request variables, and finally apply environmental limits to the runtime itself. AI models can rapidly generate logically correct code. But a senior engineer's defining value lies in understanding exactly how that code behaves when 10,000 users hit it simultaneously, and knowing how to measure, tune, and operate the live system when the pressure fractures it.